In chapter 25, we'll start talking about amines. And this will be the last chapter that I'm going to cover this semester for Organic 2. So the main feature in amines is really the lone pair of electrons on nitrogen. And that makes it a good base and a good nucleophile. So the different types of reactions that you'll see with amines are going to be either with an amine as a base or a nucleophile. Now, there's three different types of structures that are all amines, and really different functional groups come out of different reactivity. And since all of these amines mostly react the same, they're all considered amines. So we can have a primary amine, where we have a nitrogen with two hydrogens on it, for example, ethylamine. We can have a secondary amine, which is a nitrogen with only one hydrogen on it. And we can have a tertiary amine, which is a nitrogen with no hydrogens on it. So this would be ethylamine, diethylamine, or triethylamine. Now we can also make compounds that have 4 bonds to nitrogen. But now because it has 4 bonds to nitrogen, this nitrogen only has 1, 2, 3, 4 electrons that belong to it, so the nitrogen will have a positive charge on it. And these are called quaternary ammonium salts. A couple of examples could be like ammonium chloride or ammonium hydroxide. Now, ammonium hydroxide is actually a really common chemical that we have in our homes. We just call it ammonia at home. Because if you take ammonia, which is NH3, and dissolve that in water, what you get is NH4OH, or ammonium hydroxide. Now, for naming amines, we just name it with the alkyl groups, ethylamine, cyclohexylamine. If it was part of a more complicated structure, so here I have a carboxylic acid, and I have an amine on here somewhere. So 1 would be the carbonyl carbon, 1, 2, 3, 4. This would be 4-amino butanoic acid. There are also several common amines that will be important for us to know how to name, just because we'll see them in different places. So if we have a benzene ring with an amine coming off of it, that's called Annalynne. If we have an aromatic ring with a nitrogen as part of the aromatic ring, we've seen that a lot of times before now, that's pyridine. If we have a 5-membered ring with a nitrogen in it, and completely conjugated, that's pyrrole. We can also have a 5-membered ring with 2 nitrogens in it. That's imidazole. So those are all examples of common aromatic types of amines. It will also be important to think about the structure and bonding and how amines react. So if we think about nitrogen, it's going to be sp3 hybridized, which means that it will be tetrahedral. And that also means that if we have 4 different groups around it, 3 groups and a pair of electrons, that it can be chiral. And we just have an electron pair filling the 4th group. However, you might be kind of surprised by this because we didn't really talk about this in the stereochemistry chapter at all, and there's a reason for that. And the reason is, I'll draw a non-chiral version of an amine, just a simple amine here. So here's our amine with the sp3 hybrid orbital. Well, at room temperature, it rapidly interconverts through an amine that has its lone pair in a p orbital. That's sp2 hybridized, to the opposite amine that has the electron pair on the opposite side in the sp3 hybrid orbital. So the barrier for this is about 6 kilocalories per mole, which is only about 2 times the barrier for rotation around a single bond. Remember when we did the Newman projections and we looked at rotation around a sigma bond? It's only a little bit more than that. So this certainly can happen with room temperature. There's plenty of energy around for this interconversion to happen. And so even if we had a chiral amine on one side, it would rapidly interconvert back and forth across this until we had a racemic mixture. Some of the most common reactions that we'll see of amines are going to be acid-base reactions. So for example, if I have ethylamine, and I write that with HCl, what's going to happen? I'd make an ammonium salt, NH3 plus Cl minus. Now the pKa of this ammonium is 10.8, and the pKa of HCl is -7. So which one of those two is a stronger acid? Clearly HCl is a stronger acid, which means that it wants to give up its proton more. So this equilibrium lies in this direction. Let's look at a similar reaction with ethylamine and some kind of a carboxylic acid. So now I have ethylamine and acetic acid. Reacts to make the quaternary ammonium salt and acetate. So this pKa, again, just like above, is 10.8, and the pKa of acetic acid is about 4.75. So once again, this is a much stronger acid. Or about 100,000 times stronger. And so again, this equilibrium is going to lie all the way to the right.